Just take a look around you. I mean, right now. Chances are, you're seeing concrete. It's everywhere. It's the literal foundation of our modern world. But, while we live on it and in it every single day, most of us have no idea about the secret that's hidden deep inside its chemical structure. And it's a secret that has huge consequences for our planet. So let me ask you this. What if the very thing that makes concrete so incredibly strong also creates a fundamental built-in flaw? And this isn't just some hypothetical question. It's a real challenge in chemistry and engineering. And the solution? Well, the solution is pretty remarkable. And the stakes here are massive. Get a load of this number. About 7% of all global CO2 emissions come from producing cement, which is, the essential glue that holds concrete together. That is an enormous environmental footprint. So any flaw in concrete isn't just a structural problem, it's a serious climate problem. Okay, so here's the core of the issue. When cement mixes with water, it creates two main things. First, you get the stuff called calcium silicate hydrate, or CSH. This is the good stuff. It's the strong, space-filling gel that gives concrete its legendary strength. But at the exact same time, it creates a byproduct, calcium hydroxide. And this is our weak link. It's a brittle, crystalline material that's super vulnerable to chemical attacks, which can compromise the concrete from the inside out. But the problem isn't just chemical, it's physical too. On a microscopic level, concrete is a mix of that cement paste and aggregates, rocks and sand. And right where the paste meets those rocks, a weak, porous halo forms. It's called the interfacial transition zone, or ITZ. Think of it as being full of tiny little voids, creating a built-in network of weak points that runs through the entire structure. So, we've got two big problems, a chemical weak link and a physical network of gaps. Now, the solution, amazingly, doesn't come from some high-tech, futuristic lab. Nope, it comes from the smokestacks and furnaces of other industries. Let me introduce you to the mineral admixtures. These are basically byproducts, what a lot of people would just call waste from other big industrial processes. We're talking fly ash from coal plants, slag from steel mills, and silica fume from silicon production. Instead of just getting dumped in a landfill, these materials get a second life, and they hold the key to fixing concrete's fundamental flaws. And what's really brilliant is how they do it. These admixtures don't just solve one problem. They deliver a 1-2 punch, tackling both the chemical and the physical weaknesses at the exact same time with two very clever mechanisms. All right, first up is the chemical fix. It's called the pozzolanic reaction. And it's so cool. The reactive silica in these admixtures essentially hunts down that weak, vulnerable calcium hydroxide. It then reacts with it, consuming the bad stuff to create more of the good stuff, that strong, durable CSH glue we want. So here's how that transformation actually works. First, your standard cement reaction happens, creating both the strong glue and that weak byproduct. Then you introduce the mineral admixture. Its reactive silica goes in and seeks out that weak link. And in this brilliant bit of chemical jujitsu, it converts a vulnerability directly into a strength, creating even more of the good CSH glue. Second, you've got the physical fix. Here's a great way to think about it. Imagine the cement and sand particles are like tennis balls you've packed into a jar. No matter how you shake it, there are always going to be gaps between them, right? Well, the mineral admixture particles, especially something like silica fume, are incredibly fine. They're like sand, and they physically get in there and fill in all those microscopic voids, especially in that weak halo around the stones. And the results of this are just transformative. By filling these tiny voids and making that weak zone denser, you're literally blocking the highways that water and aggressive chemicals use to seep in and cause damage. You're turning a material with built-in weak points into something that's way more uniform, dense, and durable. So yeah, this is incredible science, creating a stronger material from the inside out. But the impact goes way beyond just the chemistry. This elegant solution creates what's known as a triple bottom-line win, and that means it benefits sustainability in 3 key areas. Environmentally, it's a no-brainer. You're using less cement, which means producing less CO2, and you're keeping industrial waste out of landfills. Economically, you get longer-lasting structures, which improves the whole benefit-to-cost ratio. And socially, well, it means we're building more durable, more resilient, and ultimately safer infrastructure for all of us. It's just a comprehensive victory for smarter building. But there's a catch. Of course there is. This superior performance comes with a trade-off, and it's one that really challenges the construction industry's constant need for speed. Check this out. The chart here shows that while standard cement gets strong pretty quickly and then plateaus, the blended cement starts off a little slower. But look what happens over time. It keeps getting stronger and stronger, eventually surpassing the standard stuff. That's because that pozzolanic reaction we talked about, it's a slower, more gradual process, but it continues to build strength long after the initial reaction is done. So what this really means is you have to be more patient. It requires longer curing times to let that secondary reaction work its magic and unlock the material's full, incredible potential. It's a fundamental shift from just building fast to building smart. This quote really just nails the transformation that's happening. You are fundamentally changing the material's nature. You're taking that weak, brittle crystal, the calcium hydroxide, and replacing it with a strong, amorphous gel that does a much, much better job of filling space and holding everything together. It's a complete microstructural upgrade. So let's just end on this thought, right? This whole process forces us to completely rethink what waste even means. What if the key to building the resilient, sustainable cities of the future isn't some brand new invention? What if it's been hidden in plain sight this whole time, just waiting for us in the byproducts of the very industries that built our world in the first place?